All right, this is part 2 of my solutions video for assignment 10.1, which has to do with real multiple choice problems from old AP Physics exams. In this particular problem, what we have on number 8 is where we're starting from, a disk that's rotating that counterclockwise. They tell us that counterclockwise is positive, which is what we would expect. So we have an initial velocity, angular velocity, that's counterclockwise, which is positive. Sometime later, we have two forces that are added to the system. Each force are done simultaneously. The 40 Newton force is going to cause a negative torque. The 20 Newton force is going to cause a positive torque. The net torque will be negative because 40 is greater than 20, and they're both at the same distance away from the axis of rotation. Therefore, if the torque is negative, the net torque is equal to its rotational inertia times its angular acceleration. The angular acceleration has to be negative. Oops. Okay, so I'm going to have an angular acceleration that's negative. I have an initial positive velocity, angular speed that is, and I'm going to have negative acceleration, so I'm slowing down. Which graph represents it? A is not a possibility. I have a negative initial angular velocity with a positive angular acceleration because of the slope. This one is not an option because I have a negative angular velocity initially and I have zero acceleration. This one works, positive slope, good to go. That is my answer. This one does not work because what in the world happened here? And so at any rate, this is a no. Okay. Number 9 is a very difficult problem to understand. We have a ball that's coming along with an initial momentum that's linear, hits the rod ball bounces back, and the rod takes off. There's no other objects in the system. There's no outside forces or torque, so the angular momentum initial of the system must equal the final angular momentum of the system. Well, there are two objects in the system. We have initial angular momentum of the rod plus the initial angular momentum of the sphere, so I'll call that S. That has to equal the final angular momentum of the rod plus the final angular momentum of the sphere. Okay, little s. All right. Angular momentum initial of the rod is 0. It has no initial velocity because it started at rest. The equation for the angular momentum of the sphere, we're going to talk about that in just a minute, is its moment of inertia or its rotational inertia of the sphere times its initial angular velocity, and that's of the sphere. And they wanted to know the angular momentum of the rod after the collision. So we'll just leave that LF of the rod because that's what we're looking for. And then what is the final angular momentum of the sphere? Again, it's rotational inertia of the sphere times its final angular velocity. This particle, this sphere, can be thought of as a point particle. And so the I of the sphere, the rotational moment or rotational mass, rotational inertia, is the sum of that one mass times its distance away from the axis of rotation squared. And in this problem, that distance was called d. So I'll call that d squared. So it's the mass of the sphere times its distance away from the axis of rotation squared. Now, what's its angular speed with respect to this axis of rotation at the nanosecond that it's ready to hit that board? Well, that is equal to v over r, which is, in this case, d. So I have the velocity of that sphere over d. Now let's continue on. A rod plus exactly the same thing for the end. That's m d squared v final, v initial over d. Now let's kind of clean that up a little. I got the d's that cancel. I still have v initial, and then I have a d left. Now, what is this? Whoops. This is the initial momentum, the linear momentum, times d must equal the final angular momentum of the rod, plus, same thing happens over here. I end up with m. Okay, let's see if we can do this in a way that makes sense. There we go. L final of the rod, which is what I'm looking for. Then I have m times v final times d, and that will simplify into the final momentum, linear momentum, because that's what this is, times d. Rearrange by subtracting the final momentum. Oh, hold on. Ah, I see a problem. This was in a positive direction. I'm going to assume that that's in the negative direction. That velocity was negative. So this is negative. Yes. Okay. Now, since I've subtracted it, I need to add it to both sides of the equation, and I will get P initial plus P final times D equals the final angular momentum of the rod, which would be D. Okay. I guess what the couple takeaways: a point particle, even though it's traveled linearly, does have an angular momentum. That's the first thing. The other thing is that it's just simply it's linear momentum times the distance away, or distance away from the axis of rotation. All right, I have a situation where I'm going to apply a torque and measure and see what that has as far as the impact of the angular velocity. The student uses the apparatus above, consisting of two discs that are glued together and mounted on a horizontal axle, Blocks of varying mass are hung from a string, like what we did in class, and they're released from rest. They exert different torques and are allowed to fall a fixed distance. For each block, the time of the fall t and the final angular velocity of the disc are measured. There is considerable friction between the disc and the axle. Which of the following best represents the plot? All right. This is final velocity over time. What was my initial velocity? 0. So essentially, this is the acceleration, by the way. Okay. At 0 torque that I applied, I had 0 angular acceleration. Well, that makes sense. Good. Somewhere around here, we'll call that 1 Newton meter. I still had 0 acceleration. Maybe it's 2 Newton meters. I hung another one. Still 0 acceleration. Then somewhere at 3, I hung something, and somewhere around 4, I started having acceleration, and the longer I went, or the larger my mass, or the larger my torque goes, I have an increasing angular acceleration, and it's linear. And that makes sense, because acceleration is directly proportional to torque, and just so happens, I'm pretty sure that that slope is equal to the I of rotational mass of the equipment. This is the answer, but I'm going to show you why. This distance here was how much torque was required to overcome the friction that was trying to prevent it from turning. This does not make sense, because at 0, I'm going to have 0 torque, and yet I have an acceleration. Doesn't make any sense. So in addition, this graph might make sense, except that they told us we had friction and it was considerable. And what this says is the nanosecond I put any kind of torque on it, I have acceleration. And then this one, hopefully, obviously at 0 torque, why in the world would I have acceleration? And then in addition to that, the more torque you add, the less acceleration you get. So that doesn't make sense. Okay, I have an elliptical orbit. I know that the change in momentum is equal to 0. I know the change in energy is equal to 0. And they want to know, how does this affect? Let's see. At the instant shown above, Mars is getting farther away. Okay, so we're headed this way from the sun. How does this affect the potential energy of the Mars system, sun system, and the magnitude of the angular momentum with respect to the sun? Well, we're keeping it simple. Remember, as we go farther away, there is a potential energy between the two of them. And if it's getting farther away, the potential energy is getting larger. So I only have option A and B. And then no matter what's happening, my angular momentum remains the same. Oh, Mars's angular momentum, we got to be careful. Mars's angular momentum, not the system's angular momentum. So what's happening to Mars's angular momentum? Well, that's the gosh, let's see if I can speak. It's rotational inertia times its angular speed. We know that as the potential energy due to gravity gets larger, I know that my speed has to get smaller. This one, actually, I have to think about this for a minute. I is equal to the mass of Mars times its distance away squared times that tangential velocity over r. So these are going to cancel, mRV. So it's kind of hard to say. I got to go check my answer real quick. Hold on, let me go double check. Okay. Just had a momentary lapse of reason there. Okay, once again, I know the system's potential energy is increasing. So I've got either option A or B. And so I either am increasing Mars' angular momentum or Mars's angular momentum remains the same. The sun's isn't rotating, and we know that the change in angular momentum is 0. So we're going to say that it stays the same, and that is correct. And if you're thinking to yourself, well, wait a minute, Mars's speed is slowing down because my potential energy is getting larger. So that makes sense from an energy standpoint. And you're right. Mass is constant, its radius is getting bigger, velocity is getting smaller. And so its total angular momentum for Mars is the same. Okay. Okay. A satellite that's spinning has initial rotational inertia, I0, and an angular velocity. Oh, you probably can't see what I'm writing. There you go. Angular velocity. So back up to the first one. The answer is B. Okay. All right. An angular velocity of omega initial or not, and solar panels unfold. So you have this equipment, and then all of a sudden it opens up its solar panels. Okay. Now it was spinning. And so the mass of this total mass didn't change. Okay. But its arms opened up and the mass now got further located outward. So it had a final rotational inertia IF. So let's go back and see. Its initial inertia was I sub naught, and its initial angular velocity was angular omega sub naught. Okay, the solar panels unfold. Angular, this is all internal. There's no outside forces. So I know that the I final times its angular speed final has to equal that. Now they give me this equation. So let's add A I naught, and the angular velocity final is equal to B W naught I0 I0. I remember this one being a challenge. Okay, which of the following true about the constants A and B? Okay, here's what we know. This will cancel, this will cancel, this will cancel, this will cancel. And this will be 1 is equal to A times B. All right. How many answers? A and B equal 1, possibly. I don't know. That's possible. A is greater than 1 and B is less than 1. All right, now we got to go back up here. Let's look at this. A was related to the rotational inertia, and that rotational inertia increased. So A had to go up, B had to go down. That won't work because I got to still equal 1. Okay, it's got to be B. And let me confirm. Yep, it is B, definitely, because once again, we know that the inertia, the moment of inertia went up. There's more mass that's farther away from the axis of rotation. So that coefficient in front of that original moment of inertia had to go up above 1. And then if that happens, then B has to go less because my angular speed had to go down, and the total combined have to be multiplied and equal 1. Okay, in the figures below, indicate forces acting on a rod in different situations. The length of the forces are proportional to the magnitude of the forces. Okay, in which situation is both translational and rotational in equilibrium? So, oops. Sum of the forces equals 0. Sum of the torques equals 0. Well, this has the same length of vector as that. This is creating, we'll say, a negative torque. This is creating a negative torque. The sum of the forces equals 0, but not the torques. So this is a no. Sum of the forces in B equals 0. This is creating a negative torque. This is creating a positive torque. And I don't care where you pick the axis of rotation, it's the same, so they're going to cancel each other out. So the answer is B. This one is creating a negative torque. This one is creating a negative torque. Plus they add up and have sum of the forces not equal to 0. This, excuse me, sum of the forces do not equal 0. One's larger than the other. This one, let's see. Maybe it makes it rotate that way, and that will be a negative. This one is going to make positive, but let's assume its axis of rotation is here. Doesn't matter where you pick the axis of rotation, it's still got to have 0 torque. This distance r, and this is a distance 2r, so they're not equal, they don't cancel. So the only answer is B. I got a uniform meter stick. It's balanced at its center. Which of the following shows how a 0.5 kilogram mass and a 1 kilogram mass could be hung on a meter stick so that the stick stays balanced? So we got to know that the sum of the torques is equal to 0. This side causes a positive torque. This side causes a negative torque. So the two have to equal one another. So I'm going to check 0.5 times 1, 2, 3, 4, 5. Does that equal 1.0 times 1, 2, 3, 4, 5? And the answer is no. Next one, 1, 2, 3, 4, 0.5 times 4. Does that equal 2 times 1? 2, yes. Half of 4 is 2. Is there more than 1? No, but we'll confirm the other ones are wrong. 1, 2, 3. 3 times 0.5, that's 1.5. Does that equal 1 times 2? No, it doesn't. So no. Yes. No. This one is 2 times 0.5, so that's 1. Does that equal 1, 2, 3, 4? 4 times 1, and the answer is no. Does 0.5 times 1 equal 2 times 1? And the answer is no. So we've confirmed we didn't have to do that. Once you know you're confident with your answer, circle it and move on. Okay. A system consists of 2 spheres of mass m and connected by a rod of negligible mass as shown. The system is held as its center of mass. We'll assume the center of mass is about right there. Center of mass. I'm holding it right there. What is the center of mass? Remember, it's the location at which the sum of all the torques that are created by that force of gravity is equal to 0. So there's no torque that's being created if I hold it right there. I can balance it. If I put my finger right there, it'll balance on my hand. Okay. Which of the following best explains why the system does not rotate about its center of mass as it falls? So if you hold it there and let go, there was no torque to begin with, so why would it rotate? So let's see. The Earth exerts the same gravitational force on both spheres. Well, that's not true. The force of gravity on the 2m is twice as large. So no. The Earth exerts the same gravitational force on both spheres. Generating torques that cancel out. Once again, it does not create the same gravitational force on both spheres. The Earth exerts a larger gravitational force on the 2m sphere. Yes, it does. But that sphere is closer to the center of mass and the torque cancels out. That is true. Let's look at the D. The Earth exerts a larger gravitational force on the sphere of 2m, but that sphere has more inertia and the torques cancel out. No, it doesn't. It actually has less inertia because the distance away from the axis of rotation, which is the center of mass, is squared. And so it's the distance is more important than the mass. Okay, so the answer is C. All right, I hope that makes sense. If you needed help on that.